Tell me why this amplitude modulation is highly susceptible to noise. You all know, right? Why? The amplitude gets affected, right? Because your information, your message signal is now on the amplitude of the carrier wave, yes or no? What you are transmitting is a carrier wave, high frequency carrier wave. So on the amplitude of the carrier wave, there is a message signal, right? Suppose if that amplitude is corrupted due to noise, then you're gone, right? Your information is gone and it's very difficult to recover. Have understood this, right? That is the reason your amplitude modulation is not preferred. So people want something very good, right? People want something very clear information to be transmitted. Definitely people work out in that. Have you understood this? People will not keep quiet. Requirement is actually, beginning of every invention. You know that. Okay. So the next is frequency modulation. See, ultimately your basic principles remain same. Try to understand. Ultimately your basic principles remain same. You are going to transmit carrier only. Even today, if at all you are receiving your signal, it is through the carrier only. It's through the carrier. Without carrier you can't transmit. You know that. You need to transmit a signal only using high frequency wave, carrier wave. But in that carrier wave, how do you embed your information? That's what your all transmission technology is. Hope you are understanding, right, what I am trying to tell you, right? So now, okay, one and the other way we are trying to exploit this carrier wave. You are trying to exploit this carrier wave as much as possible. Whatever the way, if you are actually trying to invent a new way of exploitation of carrier wave for the better transmission, you are a winner. You will get a Nobel Prize in that. Hope you are understanding, right? So next what? Amplitude we have exploited now. Amplitude of the carrier we have used to embed your message signal now. Now next, okay, it is giving me the problem. It is very highly susceptible to noise. What next? Next is frequency. A particular wave, a carrier wave has amplitude and also it has frequency, right? When you vary the amplitude of a carrier wave, it became amplitude modulation. At that time frequency remains same. At that time frequency remains same, right? Only amplitude varies. And you know that because of noise, that amplitude may get disturbed and you lose your message signal. Now what to exploit? Let us exploit frequency, right? Let us exploit phase of the carrier wave. Carrier wave also has a phase, right? Right? Now let us exploit the phase. That means we vary the phase of the carrier wave according to the message signal. Amplitude remains same. Let us not disturb the amplitude, because you all know the noise will affect the amplitude in a far higher way compared to the frequency, right? So what is done in frequency modulation, or we say phase modulation, that you vary the phase of the carrier wave, that is instantaneous phase of the carrier wave according to the amplitude of the message signal. Have you understood this? Ultimately you have to make a carrier signal holding the message signal, yes or no? That is what our ultimate aim is. So that when your carrier signal is transmitted, your message also will be transmitted. Hope you are understanding this. Now here we are going to exploit the phase. So what we do, instantaneous phase. Here just think this instantaneous is very important. What you did in amplitude modulation, the instantaneous amplitude of the carrier wave is varied according to the instantaneous amplitude of the message signal. That instant of time only it is getting work. Yeah, ठीक है. Actually माइनस सोचा ये दूसरा है, ये सेम है ना? नो प्रॉब्लम. जकरिया जी आप आए तो ये आया था, ठीक है. Have you understood this? So now you must, something must have been coming to your mind, right? How we are going to vary the instantaneous phase according to the message signal, right? Okay. See, you know this concept, this phase and frequency is related, you know, right? Phase. What is the phase of the phase angle of a waveform? See, these fundamentals are very important for that. If he doesn't know what is the phase angle of a waveform, entire frequency modulation he will never understand. All of you know about phase angle of a waveform, right? When you draw a waveform, okay, so what you see in a cycle, you have phase, right? 0, pi, 2 pi, 3 pi, 4 pi, what is that? Phase angle. The same phase can be written in the form of a frequency, that is rate of change of phase change, rate of change of phase. How much the phase changes per second is going to give you the frequency, right? These fundamentals are very important. You just have to know what is frequency, what is phase, what is the relation between phase and frequency. It's very important. These fundamentals will make your entire theory easy. Why a subject, a course is becoming tough? Because whenever you read that particular concept in a course, the fundamentals, if you don't know, then you cannot understand anything. Have you understood this? Okay. So you need to know the concept of phase and the concept of frequency, right? You know, phase, when you draw a sine wave, I think since many years you have been drawing a sine wave, yes or no? Yes or no? Right? This is 0, pi, 2 pi, yes or no? This is your pi by 2 and so on, yes or no? This is what phase. This is called instantaneous phase. Right? For AM, this is constant. Right? Now, for AM, we are varying only amplitude. Now, in frequency or phase modulation, or you call it as angle modulation, we are going to vary this. We are going to vary this. How do we vary this? According to the instantaneous amplitude of the message signal. So this angle variation, instantaneous angle variation, which is proportional to the message signal, is called as angle modulation. Right? Have you understood this? Okay. See, before talking about frequency modulation, we are going to start from a angle modulation. Okay, angle. See, what is this actually? Phase angle, right? Phase angle, you know. It's a phase angle. Now, this phase angle is constant before the modulation. After the modulation, this angle is varied according to the instantaneous value of the message signal. Try to understand this. Is it the concept is clear to you, or still I need to put it in different way to understand this? You can ask me, no problem. Right? Okay. Is there at least some 20% of the concept is clear for frequency modulation, for angle modulation? Okay. See, I will just tell you, see, this is your message signal, okay? Assume this is your message signal. Now, what is done in AM modulation, you all know. Are you okay thorough with this AM modulation? You all know about it, right? Now, instead of amplitude, I am going to exploit the phase angle. So, what I do at this instant, okay, whatever carrier wave I have, its phase angle is varied according to this amplitude, right. Now, next instant, the next phase angle of the carrier wave is according to the amplitude of this. Like this, every phase angle, every instantaneous phase angle of the carrier wave now holding the amplitude of the message signal. Have you understood this? This is called as angle modulation. Are you not modulating your angle there? Every instantaneous angle of the carrier wave is now modulated according to the instantaneous amplitude of the message signal. Have you understood this? This is called as angle modulation. Now, what is frequency? A rate of change of the phase angle is going to give frequency, yes or no? Yes or no? Right. So, I can relate this angle modulation to frequency, right. Hence, it is frequency modulation. We call it as frequency modulation, right. Have you understood this? Okay. So, you have phase modulation and frequency modulation. Both are actually same, right. So, if you integrate one, you get other one. If you differentiate one, you get other one. Yes or no? If I say rate of change of phase is going to give you frequency, right. What is actually in mathematics rate of change of phase? Differentiation. So, if you integrate frequency, you will get phase. These are all dual relations you need to know. Have you understood this? Right? Okay. Now, let us see one by one. See here, I am just putting you a simple picture of a message signal, carrier wave and a frequency modulated wave. Okay. Now, see here, this is your message signal. This is a message signal, simple sine wave, single tone wave, and this is your carrier. Now, you see clearly how does your FM wave looks like, right. See here, in FM wave your amplitude of the carrier remains same. You all know about it because you are not going to touch any amplitude in frequency modulation. Amplitude you are going to touch only in amplitude modulation. Now, see how the frequency varies. See here, see this amplitude, see this amplitude. The frequency will vary according to the, see you can see here frequency is high. Can you see here? At this position frequency is high. See, frequency of this carrier wave is varied according to the message signal. Now, see how does the frequency varies here. See, if you see from here to here, right, it starts from here and you can see at this position frequency is high. Can you see here? At this position frequency is high. Now, can you see at this position is this frequency is going low, yes or no? Why this frequency going low? Because this frequency at this point is proportional to this amplitude. It is lowest here. And it continues. Can you see it continues? Once again it is high here, once again it is low here, high here, it continues like that. Have you understood this? This is called as frequency modulation. Now, phase modulation. See, you don't see much difference between frequency modulation and phase modulation. See here. See, this is the carrier wave, right? Okay. Now, when the amplitude is less, your phase angle is less. Can you see here? Right? See, when your amplitude is less, see, this is the amplitude of the message signal. Can you see the phase angle of the carrier wave? This carrier wave phase angle is reduced. Can you see here? When the amplitude is peak, can you see here? Can you see here? Is the phase angle is more? Similarly, can you see here? It is varying, phase is varying. And can you see it is going high, going very low when the amplitude is less? See, your phase angle varies according to the amplitude of the message signal. When the amplitude of the message signal is less, phase angle is less. When the amplitude of the message signal is less, see, phase angle is less. Have you understood this? Now see here, in this type of modulation, if you see the phase is varying according to the message signal. Now you tell me, just think about it, how do you demodulate this? How do you demodulate a phase modulated or frequency modulated wave? How do you demodulate this? Like you have demodulated your EM wave, right? You have extracted all the peaks, right? But here you have to extract the phase. Now what is done here in demodulation, your every phase angle is converted back to the amplitude. That is going to be a demodulation. Have you understood? See, you are converting your amplitude to frequency here. Yes or no? You are converting your amplitude to phase here. You are converting your amplitude to phase, you are converting your amplitude to frequency. What is the reverse process? Tell me. Frequency to amplitude, frequency to amplitude. Have you understood this? So, this is the concept behind frequency modulation. Whatever is going to happen to the amplitude, you need not worry at all, right? In FM wave, your amplitude is constant because of the introduction of the noise. If anything happens to the amplitude of the frequency modulated wave, do you need to bother? Why? Because there is nothing in amplitude, right? You just flatten it, remove that. If anything is added to the frequency, it can be filtered using filters. Better filters are available nowadays. Better filter design is available nowadays. You can filter out all the noise. If at all you say the noise will affect to the frequency and phase also. You may ask me, sir, like AM wave, noise is affecting the amplitude, okay, that's gone. Why not it affects the frequency also here, right? It affects, but the noise frequencies can be eliminated. But if something affected to the amplitude, it cannot eliminate it, it's gone. That is the purpose. Your FM is more popular, more popular than AM, amplitude modulation. Because in FM, amplitude is constant. Anything affecting the amplitude, it is not going to affect the signal, message signal, because message signal is there in the frequency, and it is there as a variation in the phase angle. Have you understood this? This is the theory behind FM. You are using that, radio, FM radio, you are using walkie-talkie. I am going to bring walkie-talkie. In next class I will demonstrate to you all. Okay? How does FM work? This is the theory behind that FM. And this is fundamental to all communication concepts. Even if we are talking about the present day digital communication techniques, this is the fundamental. Of course, what we are discussing is all analog. Why analog? Because the signal we are considering is all analog one. We are not yet started going to digital signal. We have to do that. What we are discussing, all these concepts are for analog signals. And you know the difference between analog signal and digital signal. Have you understood this? Fine? Okay. So let us see some theoretical aspects of this. Now you understood, right, what is frequency modulation, what is phase modulation, right? Okay. It all starts from an angle modulation. Right? We say phase angle. Ultimately, we are varying phase angle. Right. So why we are calling frequency? Because there is a relation to angle. A rate of change of angle, we call it the frequency. So I will call it the frequency because frequency is more popular word. Right. Okay. So let us consider a carrier wave. This is quite normal carrier wave we are actually seeing, right? AC cos omega theta of t. See, I have not put as a here as a something like omega ct or say 2 pi f ct. I have not put it like that. Theta of t. That's what my a sine wave can be sine or cosine wave can be represented, right? A cos theta. What is a cos theta? What is a cos theta? You know, right? Theta, what is theta? It's a phase angle. And we are putting the theta in terms of frequency. Right? The same theta I can write in terms of frequency. Yes or no? I can put it in terms of frequency. Right? I can put it in terms of some phase shift. Theta plus pi by 2 I can do. This is mathematics. Right? Everything is evolved from mathematics only. This sin theta, cos theta, you know, you may be, wondering, you are studying from your 12th standard. You may be thinking, why this sin theta, cos theta always there? There is a big significance for that. Engineering and science significance on the sin theta. People are not simply, they are not fools to put the sin theta, cos theta in the science education. Sin theta, cos theta is always there. Right, okay. So it's a fun actually, understanding the sin theta, cos theta is really fun. Right. So let us consider a wave, we call it as a carrier wave, AC cos theta of t. Right. See, if you see, I have put it as cos theta of t. That means that phase angle is also a function of time. Why we are going to put it as a function of time? Because that phase varies. How that phase varies? To what proportionality that phase varies? Come on. Amplitude of the message signal. We call it as angle modulation. Right. See this, listen carefully because I am just stressing more on the fundamentals, because if you understand this, all future topics will be very easy for you. Right. See, if I take AC cos theta, simple wave, right? It's a simple wave with the phase angle theta. Have you understood this? And same theta, I can put it in terms of frequency also. I will put it as 2 pi fc. Right, I will put it as omega c, omega ct. I will put it like that. Okay. Now, this is your phase angle, right? Phase angle. I will make this phase angle as a function of time. Why I am making this theta phase angle as a function of time? Because every time instant this theta varies according to the instantaneous amplitude of the message signal. Have you understood this? That is the purpose we make your carrier signal is equal to AC cos omega theta of t. This is going to give you something called angle modulation. Yes or no? Right? Is it not going to make a justice if I call this equation as angle modulation? If theta of t varies according to the instantaneous amplitude of the message signal, if a theta of t is proportional to instantaneous amplitude of the message signal, can't I call it as an angle modulation? I can, right? Okay. So, hope you understood this equation, where theta of t is the phase angle of the carrier, which is made proportional to the modulating message signal, say m of t. Let us see how we are going to make it. See here. Let your theta of t is equal to omega ct plus phi of t. See, your phase angle of the carrier wave, how it is varied? It is varied with respect to the carrier frequency. It is not varied below the level of carrier frequency. If at all any variation happens in the phase angle of the carrier wave, it happens with respect to the constant phase angle of the carrier frequency. See, when you generate, see, I told you about this theta, right? A c cos theta. Theta is the phase angle of a carrier wave when it is not modulated. That is going to be your theta c, or I say omega ct, omega ct. If at all I vary the phase angle of the carrier wave, it is varied above that theta of t, in and above, around above omega ct. Have you understood this? A constant frequency of the carrier wave, it will remain as it is. If at all any variation happens, it will happen in and around omega ct. Have you understood this? Okay? That is what we have to remember. That is why I am writing this theta of t as a omega ct plus phi of t, omega ct plus phi of t. That means my constant frequency of that carrier frequency will remain as it is. If at all I vary any frequency, I will be doing it with respect to omega ct. That is why I am keeping this as a constant, plus phi of t, plus phi of t. And this phi of t is the term which depends on the message signal m of t. We will make this phi of t to depend on the message signal. Have you understood now? So this is a reference. Your reference frequency will always remain as a carrier frequency, that is high frequency, right? So with respect to reference frequency, you vary the phase angle phi of t. That variation we call it as phi of t, and we will make this proportional to message signal m of t. Have you understood this? Now you see, substitute this here, just substitute this here. So what you will get? AC cos omega ct plus phi of t. Have you understood this now? Now in this, which term is proportional to message signal? This term is proportional to the message signal. Can I rewrite the equation now? So I will write this particular term phi of t, phase angle only, it is a phase angle, I will put it in the phase angle only, is proportional to the message signal. So I can just change this expression, okay? I told you, depends on the instantaneous value of the message signal. Now I will just change this term, okay? Phase angle varies proportional to message signal, this varies according to the message signal. Now I can change this expression, okay? I can change this expression. Okay. See, this particular term is directly proportional to m of t. You try to understand this. It's very important, okay. Now we know that this particular term is proportional to the message signal. You all understood about this. Now next, how do you write the expression for frequency modulated wave? Right. I know this is proportional. I can write an expression, right? Since this is proportional to message signal, there will be some proportionality constant. I can just write this phi of t is equal to kf into m of t. I can write it. Yes or no? But same time, you have the relation between this phase angle and the frequency, right? How do you write it? That is the question mark here, just representing it. If you are putting it as it is, this expression will become k phase angle into m of t, that is all, right. But I want to write it in terms of frequency also. How do I write it in terms of frequency? Because there is a relation between this phase and frequency. So this kf into m of t, it's a crude term. So we have to put that in terms of frequency. That's where we are going to write a different equation for this. Have you understood this? Okay. So I will just stop here, okay, and maybe a small concept I would expect you to know and come. Okay, very simple. What is this instantaneous frequency omega or 2 pi f, 2 pi omega it, 2 pi f it? See, omega is equal to 2 pi f, you know the relation, right? Is a frequency, yes or no? Okay. Now, the instantaneous frequency of a signal, if I want to write it in terms of frequency, I have omega it, that omega it is equal to rate of change of phase angle, I told you, right, d theta of t by t, yes or no? Have you understood this? See, if I write A, okay, cos of theta of t, AC cos theta by t. What is your omega ct frequency, or I can say instantaneous frequency? This is the phase angle, right? If I want to write it in terms of frequency, if I want to write this term in terms of frequency, I want to write it in terms of frequency. So I will write it as omega it, instantaneous frequency. This is instantaneous phase angle, right? I want to write same as instantaneous frequency, then this is equal to d of theta t by dt. This relation, you never forget it. Never ever forget this. Relation between phase angle and the frequency, right? Have you understood now? See, this is your instantaneous phase, right? I told you. How can I write it as an instantaneous frequency? Just differentiate this. So how do you get, suppose if we want to get theta of t out of this, integration of dt. Never forget this. Remember. Right? So we will continue this in the next class.